Hello and welcome to a deep dive into the AWS Nitro System. My name is Ali Saidi. I'm a senior principal engineer in AWS. And today I'm going to talk to you about some of the things we've done in Nitro and why we've done them and the benefits you get from those. But I first want to start with the silicon that we're building in AWS. We've built silicon in multiple areas now, spanning I/O and data center infrastructure, core compute, and machine learning. With the Nitro system, which I'm going to spend today talking to you about, we've moved a lot of functionality away from a traditional hypervisor onto purpose-built chips that we built in AWS. This journey started back in 2013 when we moved networking off of the hypervisor with the C3 instance. And then working with a startup at the time named Annapurna Labs, which AWS would later acquire, we've been building and iterating on that ever since. And so I'm going to talk mostly about that today. But I'd like to also spend a couple minutes talking about the other silicon we've been building. With Graviton, we've built general purpose compute that provides the best price performance in EC2. And just yesterday, we announced the 4th generation of Graviton chip. Similarly, for several years now, we've been building ML chips, both for inference with Inferentia and training with Trainium. And yesterday, we announced Trainium 2, our 2nd generation of training chip that provides best-in-class price performance and efficiency for machine learning workloads. So why do we do this? Why do we spend our time building these chips? And the answer is pretty simple. We do it when we have a path to use those chips to provide you with better value. And there are a couple of reasons for this. The first is by building our own chips, we get to really specialize that hardware for the use cases within AWS. And specialization lets us tailor our designs to our particular needs. You might say, well, of course, like any chip's going to be built for your particular needs. But if you look at the way most people are going to build a chip, they want to make that chip applicable to a number of customers. They're going to add a bunch of different features, of which one customer is only going to need a handful. We get just a laser focus on the features we need to make these chips perform well in AWS and not burden them with those other features. The second is speed. By building our own chips, we get better speed of execution. And the reason for this is kind of simple. We own the end-to-end development process, from the concept of what we're going to build, all the way to what servers it's going to be in, what instances it's going to be in, and when are we going to provide it to our customers. And that just lets us bring it to you faster. But it also means that we get to design across that boundary. We can have the people who are working on the software that will end up in production actually using that software as we define and build the product. And the second one is innovation, or the third one, sorry. Building our own chips really lets us innovate more because it removes the typical silos that you have. You don't have a chip team, a card team, a server team, a hypervisor team that are different organizations. It's one big organization, and we can innovate across those boundaries. And lastly, security. Nitro's provided us a mechanism to enhance the security of our servers through a hardware root of trust, through verification of firmware on the server, and limiting interactions with the host for a narrow set of APIs. So let's dive more into the Nitro system. And Nitro is really a fundamental rethink of how virtualization should be done. At its lowest level, the Nitro system has Nitro cards. These offer networking, storage, and security functionality. And in the host, we run our Nitro hypervisor. On top of that, we run your virtual machines, and you run your applications. I'm going to talk about how this separation provides us better security and performance and has allowed us to innovate more today. But first, let's talk a little bit about how we got here. It all started with a simple question. If we applied our learnings from operating EC2 for around a decade, what would we change? What problems could we fix? And there's a lot of good suggestions, like we could improve throughput and performance. We could simplify our hypervisor. We could reduce latency and jitter so we had a bare metal-like experience. We could provide transparent encryption. We could remove operator access. We could have a narrow set of audible APIs. And really, Nitro gave us a path to implement all of these. Nitro is a combination of purpose-built hardware and software We're on our 5th generation of Nitro chip now, and we introduced this back in 2017 with the C5 instance at re:Invent. It all kind of started in 2013 with the C3 instance, though, when we first moved some networking functionality and had enhanced networking off onto an accelerator card. Over time, we expanded this to I/O, other I/O, like EBS, instance storage, and finally we built a hypervisor that we got to remove a bunch of functionality. So since 2017, we've announced something over 600 instances, all of which have been powered by the Nitro hypervisor. So here's a view of how a server looked like before the Nitro system. We have customer instances, and here they're running on a hypervisor called Zen. Now, Zen's great, but it also did a lot in this case. It did memory management and CPU scheduling, but it also did device simulation, limiters, security group enforcement, quite a bit of other things. It even has a full-blown Linux user space in this privileged DOM0. And all these resources used host CPU, introduced jitter, and so we started offloading these capabilities onto dedicated hardware. And as I mentioned, we started first with networking. So let's dive into networking. Now, we have a family of cards with Nitro. Some that do networking, some that do storage, some that do multiple things. And we throw this around, but I thought today it would be useful to actually bring one and show you. This is a Nitro card. It's got a character that kind of looks like a PCIe device. It's otherwise looks like a PCIe card. And if you plugged it into a server, you would see the ENA devices that you probably are familiar with. You would see the NVMe devices for EBS or instance storage. And that card lets us offload the VPC data plane. So when you attach an ENI to your instance, there are security groups for that ENI. There's flow logs, there's routing, and really there's all the encapsulation that's being done to create your VPC and to layer your packets on top of our software-defined network. And that's all happening on this card. All that used to happen in the hypervisor, and it got moved over. And by moving to dedicated hardware, we can increase the performance of those operations by orders of magnitude. These cards also support technologies like VPC encryption. So when you enable VPC encryption, as the packets move through the card, they're encrypted with 256-bit AES encryption in transit with no performance overhead. And this is great because you don't have to make a choice between the performance overhead or not. It just can happen transparently without one. I mentioned you've experienced these through the ENA device. When you attach an ENA device or when your system boots and it has the basic ENA device that's attached. And the ENA has two parts. One part is what's running on the card. That's the device part. And there's also the driver in your instance. And if you look at what we've done with ENA, it's been really extensible. When we announced ENA, it supported up to 10 gigabits. Since then, we went to 25 gigabits, 100 gigabits, and 200 gigabits, all with the same driver. You can stop an instance with an ENA device of 10 gigabits and start on another piece of hardware and get a 200 gigabit instance. And that's actually pretty unique. If you go and look at network drivers, there's a wide variety of them. And even a single vendor tends to iterate and have newer versions of the driver that aren't backwards compatible with the old hardware or forwards compatible with the new hardware. So with ENA, we've been able to simplify the experience of moving from generation to generation by being able to hold that device model constant for a number of years. We also have support for the ENA fabric adapter. EFA is a network with features geared towards HPC and machine learning workloads. So HPC and machine learning workloads are special. Usually something is high bandwidth or something is low latency, but machine learning and HPC workloads tend to be both high bandwidth and low latency. And so with EFA, we developed and used another AWS developed technology called the Scalable Reliable Datagram. Let's talk about that for a minute. Traditional network protocols take a single path of the network. And they're relatively slow to react to things like congestion, and even slower to react to any failures. Our networks and our data centers look something like this. They're highly connected. There's many paths that packets can take between two servers. And with that knowledge, we can detect things like congestion and failure much faster than traditional protocols can that were meant for internet scale many millisecond latencies. And that's exactly what we're doing with SRD. SRD provides a foundation where we can utilize multiple paths through our network simultaneously, allowing us to distribute bandwidth across those paths, react quickly to congestion, and significantly reduce tail latencies. And these tail latencies are really important in distributed applications and bulk synchronous applications, where you can't start the next step until all your communication is done. So even if your P50 is great, you have to wait till your P100 before the next bit of the computation starts. And that's one of the reasons that EFA is so useful for workloads, HPC-like workloads. So here, I'm showing scaling of HPC application in the number of cores. So the cores are increasing on the x-axis. And the amount of performance you're getting for those cores is increasing on the y-axis. And in a perfect world, this would be linear. As you add more cores, you'd get more performance, just 1-to-1. But you can see before EFA, in this purple line, that was the case to about 400 cores. But then the performance flattened. And even worse, as you increase the core count, it started becoming negative. You were adding more cores to solve the problem, but you were actually slowing the system down. With EFA, this is the blue line. It's not quite the red line, but it keeps scaling. It scales all the way up to over 1,000 cores. And this allows you to run larger problems in AWS. The first version of EFA supported 100 gigabits. The second version supports up to 200 gigabits. And the latency of those packets through our Nitro cards was reduced by 30%. So let's take another look at this, just with TCP. So if you're not using HPC-like network, and talk about flow hashing. So with traditional protocols like TCP, they want to take a single path of the network. And while they can deal with out-of-order packets, they can't deal with it as a common practice. So traffic takes a single path through our network. And even in a large over-provisioned network like we operate, there can be congestion from time to time. There can also be an occasional link failure. And this will cause TCP to back off its congestion control to kick in. And as I mentioned, that's really meant for internet scale latencies, not for latencies within our data center. So if you have congestion, you'll have just lower throughput. If you have a link failure, you have to wait for a timeout before you can actually reestablish that connection. And if I said, well, why can't we just use multiple paths? Well, because TCP doesn't really handle those out-of-order packets particularly well. But what we can do with SRD is send traffic down multiple paths, offload that to our Nitro cards. And that's what we're doing with ENA Express. You can enable ENA Express on a wide variety of instance sizes now. And the Nitro card takes care of sending your packets down multiple paths simultaneously, assembling them in the right order at the end, and delivering to your application without any application changes, only with a settings change. This works for both TCP and UDP. And the benefits are pretty huge. So we see a 5x increase, or up to a 5x increase in single flow bandwidth from 5 gigabits to 25 gigabits, and up to an 85% reduction in P99.9 tail latencies here. As I mentioned, it's a simple configuration. It's supported on a number of instance types now. And within your same AZ, your traffic can start using ENA Express. So if we look at how we've increased network bandwidth over time. When EC2 started, we had a 1 gigabit network. And since then, we've increased that from 1 to 10 to 25 to 50 to 100 to 200. And then with our machine learning platforms, we've gone from 400 gigabits up to 1,600 gigabits to 3.2 terabits, and even now 6.4 terabits. Just a huge amount of increase in bandwidth in a single instance. So networking is obviously a huge important piece for our workload. Storage is also an important aspect, especially for workloads like databases that need fast, consistent storage. Unlike with our networking, where we created the ENA device, with NVMe, there's a great standard driver that's very extensible. And that's what we use for our EBS storage and for our instance storage. And the Nitro cards that I just showed you expose an NVMe interface on one side. And they translate those NVMe commands to transactions to our EBS data plane. Just like with the networking side, if you would have an encrypted EBS volume, as soon as the packet transits the Nitro card or the NVMe request, it gets encrypted or decrypted there, not on the storage side. And so really the Nitro card is providing an NVMe to remote storage protocol. Here too, under the hood for a lot of different types of instances and volumes, we're using SRD as well. So we're reducing tail latencies by using multiple paths through our network to go from your instances to the EBS data plane. And very similarly, we've gone from a small number of bandwidth, 2 gigabits of EBS bandwidth, all the way up to 100 gigabits of EBS bandwidth today. Now, EBS is great. It's the right answer for a lot of customers, but you get durability, you get snapshots, but some customers also want local storage. So let me talk to you a little bit about how the Nitro card enables better local storage as well. And to do that, I really need to talk a bit about what flash is and how an SSD works. And there really are two different important parts of a flash device. The first is the NAND. This is where the bits get stored. But the NAND's kind of peculiar. And you can only write blocks of NAND that you've erased. And you have to erase blocks in usually megabyte-type chunks. So if you want to update just 1 byte, you actually need to copy a chunk of data, update that 1 byte, and store it somewhere else. And in doing so, you create some garbage. And so to abstract all of this, there's something called a flash translation layer, or FTL. And this maps the logical addresses the operating system understands to like the physical locations in the various NAND chips. It does the garbage collection that I just mentioned. It does wear leveling. And if you actually zoom out a bit, it's much closer to a write logging database than maybe you'd think. And if you go and you acquire a number of SSDs, every one of them has their own FTL. And they all behave a little bit differently. They usually do a pretty good job, but in our experience of years of operating a number of them, they can also be unpredictable at times, and you'll have garbage collection kick in at just the wrong moment. And that'll suddenly cause requests to stall. So, how can we fix this? Well, with our Nitro cards, we've integrated an FTL into them as well. And so we can provide the same FTL across a number of different devices. This provides up to 60% lower latencies, improved reliability, because we can update the firmware on those devices, and also, again, encryption, where we can encrypt all that data with an ephemeral key. So here's how our servers look like after we've moved all that I/O that I've mentioned away from the hypervisor onto dedicated hardware. You can see this DOM0 is now significantly offloaded, and many of the functions are now handled by the Nitro card. So what else can we do? So after offloading that I/O, we can go back and revisit, well, what does the hypervisor really need to do? And this led us to develop the Nitro hypervisor. It's really a lightweight hypervisor with all that functionality removed. It just does memory and CPU allocation, and then it gets out of the way. By that, what I mean is it's quiescent. If you're not asking it to do anything, It's not there. It's not consuming cycles. It's got a small size. And with that, we can also remove things like the network stack. There's no network stack on the Nitro hypervisor. There's no systemd. There's no SSH. There's no way to even connect to that hypervisor. Putting all that together, we end up getting bare metal-like performance. We've had customers run a bare metal system and compare it to a virtual system and say, there's almost no difference in performance there. Additionally, we've added the Nitro security chip to our systems. So this is a component on our motherboard that enables us to measure and confirm the contents of flash devices, like the devices that power the components that measure fan speeds or temperatures. By measuring the contents of the flash, we can confirm that it has the contents that we expect. And we can also update them out of band to make sure that we're running the latest firmware in all these components. So with that, we've migrated the management functionality as well. And we can remove DOM0 and replace the Zen hypervisor with our own lightweight hypervisor, the Nitro-based hypervisor. And if you look at the number of instances we've been able to launch, you can kind of see how much this has accelerated our pace of innovation. With this modular design and being able to take Nitro cards and put them in different systems, we've significantly increased the rate of instances. Going from 2006 to 2017, that's 11 years, we had 70 different instance types. Going from 2017 to 2023, in those 6 years, we've gone up to about 750. So over 600 instance types in those 6 years. And these instance types provide you options with high networking, with storage, with different processor architectures, all so you can optimize your costs for your specific use case. So let's talk about the security aspects of the Nitro system. Keeping customers' workloads secure and confidential is our top priority. And security is a shared responsibility. AWS is responsible for the security of the cloud. We operate, manage, and control the components from the host software, the virtualization layer, down to the physical security of the facilities that those systems are in. And you, our customers, are responsible for security in the cloud. What I mean by that is for something like EC2, keeping your OS up to date, configuring things like security groups appropriately, and just general management of the guest OS. In the past couple of years, there's been a lot of interest in the world of confidential computing, and also some confusion. And usually the first question I ask people is, well, what are you protecting data from? And usually the answer is they want to protect the code and data from other people other than them, be that other customers or a cloud service provider. And this is called Dimension 1. And by the way we architected Nitro, we built mechanisms to protect customer code and data from outside access. It's really fundamental to the design decisions we made when we built Nitro. First, there's a physical separation from where your code's running to where our encapsulation and infrastructure is running on the Nitro card versus the host. When our systems boot up, I mentioned the Nitro security chip that measures the firmware, confirms its contents. Our Nitro controllers boot, measure themselves, and use that to unlock their storage and allow the system to boot. With the Nitro system, we're able to live update the components in there without downtime. This software is developed by a globally distributed set of teams with multi-party code reviews. It's cryptographically signed by an automated build pipeline that engineers don't have access to, and then deployed by our deployment service, which defines the deployment velocity, policy, and where changes can be deployed, and then rolls back if there's any anomalies. But most importantly, there's no remote access to these systems. There's no SSH server or anything like an SSH server. There's only an API that's encrypted, authenticated, authorized, and logged. And none of these APIs provide access to customer content. The other dimension people talk about is dividing customer workloads into a more and a less trusted components. So this separation can limit your operator access, but also compartmentalize bugs in your application to not expose secrets. So a common case here can be to put certificates into an enclave and then only allow the parent process to request signing with those certificates. So you have all the protections of the Nitro-based instances, but enclaves give you a couple more things. An enclave is an instance where the parent process has donated some memory and some CPUs to create a new instance. But that instance doesn't have a couple of things. It doesn't have networking. It doesn't have any persistent storage. It just has a small straw that goes back to the parent. And this makes it a separate, highly constrained VM. The parent can't SSH into it. The parent can't control or inspect the processes or applications running in it. And so in that enclave, you can have secrets and do things like request signing with those secrets or process data where the bulk of the application can't access it. We've also been adding some other features, security features to Nitro. One is secure boot. So AMIs today are immutable. When you have an AMI and you create one, it can't be changed. But customers have been using UEFI Secure Boot in a number of areas and asked us if we could support that. And with Secure Boot, the firmware measures, or chain measures, the bootloader, the operating system, and then compares those measurements to UEFI variables. And what this ultimately provides is more defense in depth to secure software from threats that persist to reboots. So if for some reason the software on the root volume has changed, it can be detected with UEFI Secure Boot. Another thing we've added is a TPM device. So a TPM is a trusted platform module. The Nitro TPM exposes a standard TPM2 conforming device that, as part of the boot process, can extend measurements, tie the platform identity into it, and use those measurements to generate cryptographic data that can then be used for other applications. People have applications that rely on Lux or BitLocker or others, and this is a way to use those. Nitro's delivered a unique architecture that restricts operator access to customer data, and we've written down a lot of the aspects of this in this white paper called "The Security Design of the Nitro System." It's available on the AWS website. And more recently, the NCC group has performed an independent architecture review of the Nitro system and found that there's no mechanism for a cloud service provider employee to log in to the underlying host or to access customer content stored in instance storage and encrypted EBS volumes. So, a really powerful statement. So let's put some of this together. We've talked about various aspects of it. We talked about networking, we talked about storage, we talked about security. How does it all work? So to use as an example, I'm going to start with a Graviton 3 server. Graviton 3 is a little bit odd in that it has 3 sockets. Typically, a server has 1 or 2, but Graviton 3 has 3. And the reason for that is really that for a certain power envelope of a rack, we could just stick more processors in there. So we did. The end-to-end ownership of both Graviton and the Nitro system allowed us to develop a Nitro card that could not talk to 1 socket or 2 sockets, but to 3. And all these 3 sockets have independent life cycles that are managed by the Nitro card. They could be bare metal instances, they could be virtual instances. So I'm going to use this picture for the next few slides. On the left, we have the EC2 control plane. If you start an instance and call the run instances API, you're going to talk to the EC2 control plane. And there are a number of services in there to do things like authenticate your request, identify a pool of capacity that meets the requirements for what you've asked for, the availability zone, any other, the size, the instance type. And ultimately identify a specific host that can run your VM. On the right here, I'm showing a Nitro controller and some Nitro cards. And in this example, there's 3 VMs running, each with 64 cores, 128 gigabytes of RAM, 30 gigabits of networking, and 20 gigabits of EBS. So let's walk through how an instance gets launched. Your API call comes into the EC2 control plane, and we find a specific host to target for that. And the control plane makes a request to the Nitro controller. It says, please allocate some resources. In this case, 64 cores, 120 gigabytes of RAM. Then Nitro controller talks to the hypervisor and requests that those resources be allocated and reserved. When that's set up, the control plane then asks the Nitro cards to please attach the fundamental devices, your ENA device, your boot volume, any other volumes or network adapters that you've asked for as part of the instance. Those get created and connected to the Nitro cards. This all happens over PCIe SR-IOV. So there's no hypervisor interaction between accessing those devices and the actual communication with them. And then a last API call. This says start the instance. The instance starts, it looks at its EBS volume, it finds the code to boot, and it starts booting it. And your instance starts running. It boots the OS, it talks to the network, and it's available. Now, because we've moved all that functionality off of the hypervisor, if you start a bare metal instance, the same thing happens, except there's no hypervisor. You just get the whole host. And instead of telling the hypervisor to start the instance, we just boot up the main CPU. A lot of people think of a CPU as the nexus of a system. But in our servers, we've kind of turned that around. The Nitro card has become the nexus of the system. It controls when the host boots. So because of all the functionality for VBC, EBS are handled outside of the hypervisor, you get the same experience. If you're running on a bare metal system or on a virtual machine, you get the same devices, you get the same configurability like security groups. And we can take that even further. For a couple of years now, we've had Apple Mac-based instances. And here, too, if you open up one of these servers, you'd find there's actually a Mac Mini sitting in a server, and there's a Nitro card. And Macs support Thunderbolt. Thunderbolt's just really another way to transport PCIe. So there's a Thunderbolt to PCI bridge, a Nitro card, all in a server, and a little solenoid to push the power button on the host. But this means that your developers can get access to Apple machines in the same environment that you expect with EC2. You can have security groups. You can have the elasticity, configurability, and monitoring that you've come to expect. So actually, I've flown through this. And as I wrap up, I want to share with you today that we're announcing a new compute knowledge digital badge and learning path on AWS Skill Builder. So this is a way to gain and demonstrate compute knowledge and skills. And with that, I thank you for spending time with me today. I'll be hanging around here for a little while, and I'm happy to take any questions offline. Thank you.